Welcome to the second part of Unit 7 for AP Physics 2. In this section, we're going to learn about atomic physics. We'll start off with a very brief review of different models of the atom, and then we'll talk about how the phenomenon of atomic spectra led to the model of the atom that was developed in the early 20th century. So here are some important milestones in atomic structure. Different models of the atom. In the 5th century BCE, Greek philosophers, including Democritus, hypothesized that matter consisted of atoms. This is more of a philosophical viewpoint. They considered the atom to be the smallest that something could be made of. In fact, the word atom means cannot be cut. In 1808, John Dalton used this idea of atoms to explain many of the principles of chemistry that were known at the time. And so for about 100 years or so, the atomic theory, the idea that the atom was the smallest piece of matter, held sway. But in 1897, J.J. Thomson showed that cathode rays, which were known to be emitted by atoms, were actually particles themselves. In other words, the atom had smaller parts, so it was actually possible to split the atom into smaller pieces. Now, these particles, these cathode rays, were shown to be negatively charged, which meant that the part of the atom, by conservation of charge, must be positively charged, since you can't just create negative charge by itself. And the original atom was electrically neutral. So in 1910, Rutherford used a gold foil experiment, showed that the positive charge in the atom must be confined to a tiny area in the middle of the atom. Rutherford's experiment involved taking helium nuclei, what we now know are helium nuclei, at the time they just called them alpha particles, and firing them at a very, very, very thin gold foil, and finding out that rather than the helium nuclei bouncing off in a kind of a random pattern, they actually mostly went straight through the gold foil, but a very, very few of them, the ones that didn't go through the gold foil, often bounced straight back. And that's what led Rutherford, using conservation of momentum, to conclude that the nucleus itself, this positive part of the atom, must be tiny. So in 1913, Niels Bohr proposed a model of the atom that explained some of these phenomenon, and also explained why atoms displayed absorption and emission spectra. So by absorption and emission spectra, we're referring to this phenomenon that was discovered, that when you heat certain substances, they give off light, but the light they give off is not every possible wavelength of light. Only certain wavelengths of light are emitted. In fact, the wavelengths of light emitted by a given element are kind of a fingerprint for that element. Now, the way that one observes these different wavelengths of light being emitted from different elements is very similar to what we did earlier this year with our diffraction gratings. As you know, the formula for the angle that the first peak of a given wavelength of light makes with the central maximum is dependent on the wavelength. And so if you pass light from these elements through a diffraction grating, and then you observe the resulting pattern on the screen by measuring the distance from the central maximum to the different first order interference fringes, you can determine the wavelength of light. Some elements have very few wavelengths, at least in the visible light range, and some will have a whole bunch of wavelengths in the visible light range. You could also get an absorption spectrum. What happens here is if you take a light that contains all the colors of the rainbow and pass it through a gas of a certain element, the same frequencies or wavelengths of light that are emitted by the element when it's heated will be the ones that that element will absorb when you pass white light through it. Now, these different light spectra emitted by different elements were studied in detail in the 19th century, particularly hydrogen. Johann Balmer discovered that the wavelengths of visible light that were emitted by a hydrogen atom were given by a formula like this, where you have 1 over the wavelength of light being equal to a constant times 1 over 2 squared minus 1 over n squared, where n is 3, 4, 5, etc. Now you might be wondering, why did I write it 1 over 2 squared? Well, you'll see about that when we look at the other formulas here. But keep in mind, these were just experimental formulas. They didn't understand why light was emitted like this. They just figured out through very rigorous math that these formulas fit the colors of light emitted by hydrogen. As an exercise, why don't you try to calculate the first 3 wavelengths in the Balmer series? That means you're going to substitute in the formula I just gave you. N is equal to 3, n is equal to 4, and n is equal to 5. So if you have n is equal to 3, you should end up with a wavelength of 6.56 times 10 to the minus 7 meters. N is equal to 4 is 4.86 times 10 to the minus 7 meters. And n is equal to 5 is 4.34 times 10 to the minus 7 meters. These are all in the visible wavelength range. Now, the constant from the Balmer formula is known as the Rydberg constant. And it's called that because Johannes Rydberg figured out a way to combine not only the Balmer series of lines, series of wavelengths, but also ones that appeared in the ultraviolet region and ones that appeared in the infrared region. The ultraviolet lines are called the Lyman series, and the infrared lines are called the Paschen series. And here is Rydberg's single formula. You'll notice it is the exact same form as the Balmer formula, but now instead of having 1 over 2 squared, we have 1 over n squared, n1, and n1 can be any number, any integer from 1, 2, 3, 4, etc. But n2 must be a larger integer than n1 so that the formula ends up being positive. If you notice, you have 1 over n1 squared minus 1 over n2 squared. As long as n2 is larger than n1, then your formula is going to give you a positive value for 1 over the wavelength. Now, in 1913, Niels Bohr was able to publish a model for the hydrogen atom that explained the observed spectra of the atom by assuming that the electrons, the negative particles, are orbiting the nucleus at certain fixed distances away from the nucleus. And making that assumption, he was able to explain why we only see certain frequencies of light being emitted by the atom. The central idea is that these different orbital distances correspond to certain energies. And so although Bohr's model of the atom is not the currently accepted model of the atom, it was the first to really quantize the different possible energies that an atom can take on. So we'll first look at the basic ideas behind Bohr's model, and then we'll look in greater detail at his calculation. Here's the basic idea. We know that an atom's electrons are attracted to its nucleus by the electromagnetic force. It's going to require energy to separate them, which means that the system has potential energy. And if the electrons are thought to be orbiting around the nucleus, then that means the electron also has kinetic energy. So the farther away the electron is from the nucleus, the greater total system energy is going to have. Not only the potential energy will be greater as the electron goes farther away, but as we will see, the kinetic energy that the electron has to have in order to orbit in a circular pattern must be greater the farther away it gets from the nucleus. To get an idea of what's going on here when the light is emitted or absorbed by atoms, why don't you run the PhET simulation, the models of the hydrogen atom. When you're doing that, set it to show you what happens in the Bohr model. And then in this simulation, they're going to have different frequencies of light will pass by the atom. And the questions you should ask yourself are, does every possible frequency of light get absorbed by the atom? And what happens when light of an absorption frequency shines on the atom? And then what frequencies of light are emitted by the atom? So take a look at those questions and see if you can observe what's going on here by looking at Bohr's model of the hydrogen atom in this simulation.